Fluid dynamics. How are flows classified? There are multiple factors that can be used to classify a flow. These include the dimension of the flow. Flows can be one-dimensional, two-dimensional, and three-dimensional. Variations in time. If the flow changes over time, it is classified as unsteady. If the flow remains consistent over time, it is classified as steady. Variations in space. If there are no variations in water depth, slope, discharge, etc. along the channel, the flow is uniform. The flow regime. This is used to classify the flow as supercritical, critical, or subcritical. The flow type. This is used to classify the flow as laminar or turbulent. The dimension of the flow. Flows can be classified as one-dimensional, two-dimensional, or three-dimensional. A one-dimensional flow only has variations in the flow along one spatial direction. A two-dimensional flow has variations in the direction of the flow and across the flow. A three-dimensional flow has variations in all three spatial directions. Variations in time. If there are no variations in the flow over time, the flow is steady. Otherwise, the flow is classified as unsteady. Variations in space. A uniform flow has no along-channel variations in any of the variables. A non-uniform flow has variations in one or more of the variables. Slowly varying flows have gradual variations, which means that pressure is usually hydrostatic and streamlines are straight. Rapidly varying flows have rapid variations, which means that pressure is usually not hydrostatic and streamlines are curved. The flow regime. Keep in mind that this is only applicable to open channel flows. The flow regime is classified by the Froude number, which is defined as the ratio of the mean flow velocity and the shallow water wave velocity. Supercritical flows occur at regions where the Froude number is greater than 1. Critical flows occur when the Froude number equals 1. Subcritical flows occur where the Froude number is less than 1. A hydraulic jump forms at the transition between super and subcritical flow. The flow type. Flows can be classified by the Reynolds number. The Reynolds number is calculated by dividing the velocity times the characteristic length by the kinematic viscosity. In open channel flows, the characteristic length is the hydraulic radius. If the Reynolds number is less than the critical value, which depends on the context of the flow is laminar. If the Reynolds number is much greater than the critical value, the flow is turbulent. Here are some key terms and ideas in fluid dynamics. Upstream refers to the direction opposite to the flow. Downstream refers to the direction that follows the flow direction. The frame of reference of the observer can affect the perceived steadiness of the flow. Ideal fluids are fluids that only experience normal stresses. This means that shear forces can be ignored and friction can be ignored when drawing streamlines. Real fluids experience friction and can create boundary layers. Boundary layers are regions where the flow has a large change in velocity. The no-slip condition states that the velocity of a fluid is identical to the boundary velocity at the boundary. If the boundary is stationary, this is 0. The vena contracta is the point in the fluid flow where the stream cross-section is the smallest. Within this region, the streamlines are locally straight. A stagnation point is the location where the flow has 0 velocity. The x-momentum of a fluid particle is ρu and can be interpreted as momentum density. Approaches to describing fluid motion. There are two main approaches to describing fluid motion, the Lagrangian approach and the Eulerian approach. In the Lagrangian approach, small elements of fluid are tracked over time. In the Eulerian approach, a control volume is drawn around a fluid system and the flow into and out of surfaces are considered. Streamlines. Streamlines are continuous lines that are everywhere tangential to the instantaneous flow velocity. There are 6 fundamental properties of streamlines. Streamlines cannot cross. Fluid cannot cross a streamline. Streamlines can meet at a point. Locally, the flow must run parallel to solid boundaries. Therefore, any solid boundary is a streamline. 2 adjacent boundaries may be thought of as a stream tube. The fluid velocity is correlated to the inverse of the streamline spacing. Obstacles that are not streamlined are called bluff bodies. When the flow hits a bluff body, it will separate from the solid boundary. This creates zones of flow separation, flow reattachment, and recirculation. When the flow hits a streamlined body, the streamlines will not separate. Pressure distributions. If the vertical acceleration in a moving fluid is negligibly small, we can assume that the pressure distribution is hydrostatic. The vertical acceleration is negligible when the streamlines are nearly horizontal without significant curvature. In horizontal parallel streamlines, the horizontal pressure distribution is constant and the vertical pressure distribution is hydrostatic. In closed conduits, for example pipes and ducts, the pressure is constant. Fluxes. Fluxes are the rate at which a substance flows through a surface. Volume flux, or discharge, is calculated with Q equals UA, where U is the fluid velocity and A is the cross-sectional area. Velocity profiles. The way the velocity of a fluid changes as a function of depth is known as the fluid's velocity profile. The mean velocity can be calculated with U equals QA, where Q is the volume flux and A is the cross-sectional area. Alternatively, it can also be calculated with the integral of U dA over the integral of dA. Fluxes can be calculated by integrating specific parameters denoted x across the velocity profile multiplied by the velocity. The mass flux is calculated with the integral of rho U dA. The momentum flux is calculated with the integral of rho U squared dA. The kinetic energy flux is calculated with the integral of half rho U cubed dA. When the exact velocity profile is not given, these fluxes can be approximated. Mass flux is approximated with the formula rho UA, which equals rho Q. Momentum flux is approximated with the formula rho U squared A, which equals rho QU. Kinetic energy flux is approximated with the formula half rho U cubed A, which equals half rho QU squared. Dynamic and kinematic viscosity. Viscosity is a measure of how much resistance a fluid has to shear. The dynamic viscosity mu is related to the shear stress by tau equals mu du by dx. Fluids that satisfy this relation are known as Newtonian fluids. The implications of this relation are that any amount of shear stress will cause a flow. And if there is no velocity gradient, there can be no shearing stress. The kinematic viscosity nu is related to the dynamic viscosity by nu equals mu over rho. Dynamic viscosity is used when dealing with forces. Kinematic viscosity is used when dealing with fluid motion. Conservation. The general form of the conservation equation for a property of a fluid is storage equals fluxes in minus fluxes out plus sources minus sinks. Volume conservation requires that the volume flux in equals the volume flux out. In other words, U1A1 equals U2A2. Mass conservation requires that the mass flux in equals the mass flux out. In other words, rho U1A1 equals rho U2A2. Newton's second law. Newton's second law states that the time rate of change of the momentum is equal to the sum of the forces. This is useful when considering the force exerted by fluids. Bernoulli's equation. Bernoulli's equation can be used to describe the energy at a point in the flow of a fluid. The Bernoulli equation is total energy equals the pressure plus the gravitational potential energy plus the kinetic energy. This equation can be converted into an alternate form where each term has units of length. These terms are called heads. The total energy head equals the pressure head plus the elevation head plus the velocity head. The pressure head represents the height of the column of fluid required to produce the pressure P. The pressure head plus the elevation head together are known as the piezometric head. In a hydrostatic distribution, the piezometric head remains constant in the vertical. These equations equal a constant along a streamline, as the energy at any point along a streamline is constant. The assumptions required to use Bernoulli's equation are: the flow is steady, the flow has a constant density, and the flow is frictionless. Graphically, the total energy head and the piezometric head can be represented by the energy grade line and the hydraulic grade line. The difference between the two lines represents the velocity head. Head losses. There are two types of head losses in a fluid flow: major and minor losses. Major losses include losses due to friction with the pipe wall. The amount of head lost is equal to F L over D U squared over 2G, where F is the friction coefficient of the pipe, L is the length of the pipe, and D is the diameter of the pipe. Minor losses include losses due to pipe bends, contractions, entries, exits, fittings, and valves. The amount of head lost takes the form xi U squared over 2G, where xi is the loss coefficient. Specifically, exit losses when a pipe discharges into a reservoir take the form U squared over 2G. This is because all kinetic energy is lost. Causes of fluid motion. A fluid will move when a non-zero resultant force acts upon it. This means changes in pressure can cause fluid motion. Gravity causes fluids to move. Density differences causes fluids to move. Friction or viscosity can cause fluids to move. Forces exerted by a solid surface cause fluid motion. Measurement devices. Using pressures, a pitot-static tube can measure the velocity of a fluid. Also using fluid pressures, a Venturi tube can be used to measure the volume flux in a pipe. Pumps and turbines. Pumps provide energy to the fluid flow, and turbines extract energy from the flow. In terms of the energy grade line, pumps increase the energy head, so the energy grade line increases in height. The formula for power generated by a turbine is P equals rho G delta H cube, where delta H is the change in energy head. Open channel flows. Flows in open channels have a free surface. This causes the cross-sectional variables, for example the cross-sectional area, the width, and the wetted perimeter, to become functions of the water depth. The definition of an open channel flow is a flow of fluid with a free surface that is driven along a conduit by gravity. In an open channel, the hydraulic mean depth is the cross-sectional area divided by the width. The hydraulic radius is the cross-sectional area divided by the wetted perimeter. To calculate the average velocity of a flow in an open channel, Chazy's equation is used. U equals C root Rs, where C is the Chazy coefficient, R is the hydraulic radius, and S is the slope of the channel bed.